a monumental preparation. 106,000 hours. The sheer scale of preparation for the Lincoln Eastern Bypass Rail Bridge installation is staggering, accumulating over 106,000 hours. The groundwork involved intricate planning, designing, logistics management, material testing, and labor force organization. The 72-hour blockade, the final installation process, required a precise, round-the-clock operation. A 72-hour blockade. During this period, rail traffic was entirely halted to allow the construction team unobstructed access to the site. This timeframe represented a high-stakes deadline for completing some of the most complex parts of the project. Within this limited window, the team removed the old infrastructure, excavated large quantities of earth, installed the bridge, and restored the surrounding areas, ensuring that the rail line would resume normal operations as planned. One of the most demanding tasks during the blockade was excavating over 7,500 tons of earth to make way for the bridge's massive structure. This phase involved using high-capacity machinery to remove and transport large volumes of soil and debris, a feat that required impeccable timing and coordination. The core structural elements of the bridge consisted of two massive steel beams, each weighing approximately 107 tons. Transporting and positioning these beams was a logistical challenge in itself, demanding specialized equipment and careful coordination to ensure the beams were handled without risk to the team or the structure. The installation required incredible precision to meet strict engineering standards, ensuring that the beams could support the weight and stresses of rail traffic once in operation. Adding to the complexity of the operation, 43 meters of cutting and burning work had to be completed during wind gusts that reached up to 48.8 miles per hour. The bridge installation faced challenging conditions, with gusts reaching 48.8 miles per hour, requiring precise handling and rigorous safety measures to ensure stability. The 86-meter skid track was engineered to guide the bridge components precisely into position, ensuring smooth movement and exact alignment. The project required an enormous quantity of 100,000 tons of stone to create temporary access platforms and foundations essential for the bridge installation. This stone served multiple purposes. It provided a stable base for heavy machinery, ensured safe movement of workers, and facilitated the transportation of materials to the installation site. The careful placement of this stone was crucial for maintaining structural integrity during the intense 72-hour blockade. The use of durable, high-quality stone not only supported the immediate needs of the project, but also ensured long-term stability for the bridge's foundation, demonstrating a commitment to robust engineering practices. Each sill unit, weighing 50 tons, was designed to provide a robust foundation for the bridge structure. These heavy-duty components distributed the weight of the bridge evenly across the underlying supports. Their substantial mass ensured stability, enabling the bridge to withstand the dynamic loads imposed by rail traffic and environmental conditions. One of the project's most remarkable elements was the use of the Mammaloff, a 604-ton hydraulic lifting device that allowed the team to position the bridge structure with remarkable precision. The entire skidding process lasted 109 minutes, during which the bridge components were maneuvered into their final position on the foundations. This complex operation required careful monitoring and control to ensure that each component aligned perfectly with the others. The construction of the Lincoln Eastern Bypass Rail Bridge required meticulous attention to detail, with over 6,000 bolts securing various components together. The bridge deck, measuring 40.5 meters in length, featured over 1,300 individual vent components to enhance drainage and structural integrity. Each of these components was precisely aligned with 3,300 countersunk holes, allowing for a flush and secure fit that minimized potential weak points. This careful assembly ensured that the deck would withstand the forces exerted by passing trains, contributing to the overall safety and longevity of the bridge. During the critical 72-hour blockade for the Lincoln Eastern Bypass Rail Bridge installation, the team dedicated an impressive 3,660 work hours to complete essential tasks. This intense period required around-the-clock effort from skilled workers, engineers, and machinery operators, all focused on ensuring the installation proceeded smoothly and on schedule. Each hour was planned, with tasks such as excavation, the positioning of steel beams, and the installation of sill units being carried out in a coordinated manner. The workforce operated in shifts, allowing for continuous progress despite the demanding nature of the work. This period saw the mobilization of heavy machinery and equipment to handle the significant loads, including the 107-ton steel beams and 100,000 tons of stone for foundations. The team's ability to complete such a high volume of work under time constraints and challenging weather conditions exemplifies their dedication and expertise, ultimately leading to the successful completion of the bridge project. To complete the bridge, around 800 tons of ballast and 288 new sleepers were laid on the bridge deck, creating a stable bed for the rails. Ballast is crucial for rail stability as it absorbs vibrations and distributes the weight of the train evenly across the bridge deck. The sleepers, which support the rails, were carefully placed to ensure the track remains level and secure. The Lincoln Eastern Bypass Rail Bridge stands as a testament to what can be achieved through thorough preparation, cutting-edge technology, and skilled teamwork. With over 106,000 hours of preparation, 7,500 tons of earth moved, 107-ton steel beams, and the tireless dedication of countless engineers and workers, the bridge is now a critical piece of infrastructure, supporting efficient transport and connectivity in the region. This project encapsulates the resilience and precision that modern engineering demands. Each step, from the 72-hour blockade to the final finishing touches, demonstrates the team's commitment to excellence, safety, and precision in the face of challenging conditions and tight deadlines. The Lincoln Eastern Bypass Rail Bridge is more than just a bridge. It's a symbol of human ingenuity and collaboration, overcoming obstacles to shape infrastructure for future generations. Construction of the road bridge in Torun, a picturesque city in northern Poland, renowned for its medieval architecture and as the birthplace of the astronomer Nicolaus Copernicus, has seen significant infrastructural developments in recent years. Among these, the construction of a new road bridge has played a crucial role in enhancing the city's connectivity and addressing traffic congestion issues. This article explores the construction of the road bridge in Torun, detailing its design, engineering challenges, construction phases, and the impact it has on the city and its inhabitants. The Torun Road Bridge, officially named the Bridge of Unity, was conceptualized as a response to increasing traffic demands and the need for efficient transportation routes across the Vistula River. The bridge serves as a critical link between the northern and southern parts of the city, facilitating the movement of vehicles, pedestrians, and cyclists. It is designed to improve local accessibility while contributing to the broader regional transportation network. Type: the bridge is a cable-stayed structure characterized by its elegant design and minimalistic aesthetic. Cable-stayed bridges are known for their ability to span long distances while requiring less material than traditional arch or beam bridges. Length: the total length of the bridge is approximately 1,000 meters, with the main span measuring 300 meters. Lanes: the bridge accommodates 4 lanes of vehicular traffic, along with dedicated pedestrian and cycling paths on either side. Materials: the Primary materials used in construction include high-strength concrete, steel cables, and reinforced materials to ensure durability and resilience against environmental factors. Design and planning. The design process for the Torun Road Bridge involved extensive planning and consultation with various stakeholders, including city officials, engineers, and the local community. The design team sought to create a structure that would blend seamlessly with the city's historic character while addressing modern transportation needs. An environmental impact assessment was conducted to evaluate the potential effects of the bridge on the local ecosystem. This included studies on wildlife habitats, water quality, and noise pollution. Mitigation measures were incorporated into the design, such as noise barriers and landscaping, to enhance the surrounding environment. Traffic analysis. Comprehensive traffic studies were performed to understand current and projected traffic patterns. This analysis informed decisions about lane configurations, traffic signals, and access points. The goal was to reduce congestion in the city center and improve overall traffic flow in the region. Public consultations were held to gather feedback from residents and local businesses. This engagement helped address concerns and incorporate suggestions into the design. Educational sessions were conducted to inform the public about the benefits of the new bridge and its role in enhancing connectivity. Construction phases. The construction of the road bridge in Torun was carried out in several phases, each requiring careful coordination and execution to minimize disruption to the community and the environment. Initial work involved clearing the construction site, which included relocating utilities, removing vegetation, and conducting soil stabilization. A temporary access road was constructed to facilitate the movement of heavy machinery and materials to the site. Foundation work. The foundation for the bridge required significant excavation and reinforcement due to the varying soil conditions along the Vistula River. Deep foundations were established using bored piles, which were drilled deep into the ground to reach stable soil layers. This ensured a solid base for the bridge's towers. Concrete was poured into the drilled holes, and rebar cages were installed to enhance structural integrity. Construction of the towers. The main towers, which support the cable-stayed design, were constructed using high-strength concrete. Each tower was designed to withstand significant vertical and lateral loads. Formwork was used to shape the concrete, and cranes were employed to lift heavy materials into place. The construction team ensured that safety protocols were strictly followed during this phase. Once the towers were complete, the next phase involved the installation of the steel cables that would support the bridge deck. These cables were tensioned to create the characteristic profile of the cable-stayed bridge. The bridge deck was constructed using prefabricated concrete segments that were transported to the site and placed using cranes. The segments were then connected and reinforced to form a continuous surface. Finishing touches. After the main structure was completed, work focused on finalizing the roadway, including asphalt paving, installation of traffic signals, and road markings. Pedestrian and cycling paths were constructed alongside the main roadway, promoting multimodal transportation options. Landscaping around the bridge was completed to enhance the aesthetic appeal and integrate the structure into the surrounding environment. Challenges faced. The construction of the road bridge in Torun was not without its challenges. Several factors tested the project management team's ability to adhere to timelines and budgets. Adverse weather conditions, including heavy rains and strong winds, occasionally halted construction activities. The project team had to implement flexible scheduling to accommodate these interruptions. Geotechnical issues. The variable soil conditions along the river posed significant challenges during foundation work. Additional geotechnical assessments were needed, leading to modifications in the foundation design to ensure stability. Community impact. Construction activities caused temporary disruptions to local traffic patterns, leading to concerns among residents and businesses. The project team worked closely with local authorities to implement detours and communicate updates to the community. Impact and benefits. The completion of the Torun Road Bridge has had a profound impact on the city and its residents. Key benefits include: the bridge significantly enhances connectivity between the northern and southern parts of Torun, reducing reducing travel times for commuters and freight traffic. Economic growth. By improving access to key areas of the city, the bridge supports local businesses and encourages economic development in the region. Increased traffic flow has led to higher visibility and accessibility for commercial enterprises. Sustainability. The design promotes sustainable transportation options, encouraging walking and cycling, thus contributing to reduced vehicular emissions. Cultural significance. The bridge has become a landmark in Torun, combining modern engineering with the city's historical context. It serves not only as a functional structure, but also as a symbol of progress and innovation. The construction of the road bridge in Torun represents a significant achievement in urban infrastructure development. Through careful planning, innovative engineering, and community engagement, the project has successfully addressed the city's transportation needs while enhancing its aesthetic and cultural appeal. As Torun continues to grow and evolve, the Bridge of Unity stands as a testament to the city's commitment to modernity and sustainability, paving the way for a brighter future for its residents.
The Third Bosphorus Bridge, also known as the Yavuz Sultan Selim Bridge, is a remarkable engineering marvel that connects the continents of Asia and Europe over the Bosphorus Straits in Istanbul, Turkey. Construction of this impressive bridge took place between March 2015 and March 2016, and it was built with the collaboration of a predominantly Turkish team of engineers. In March 2015, the assembly of a 1,000-ton capacity crane, named Derrick Crane, was completed to facilitate the installation of the third steel deck, which weighed 940 tons, had a length of 24 meters, and a width of 59 meters. This massive steel deck was lowered to the shore by a giant floating crane with a carrying capacity of 1,800 tons. The successful operation required the expertise and collaboration of the construction teams, given the complexity and precision involved in handling such large and heavy structures. The bridge boasts a unique design, featuring 8 lanes of motorway and 2 lanes of railway situated at the same level. Its aesthetic and technical features are set to make it one of the most important and eye-catching bridges in the world. One of its standout features is its width, measuring an impressive 59 meters, making it the widest suspension bridge globally. Moreover, it holds the record for being the longest spanning suspension bridge in the world with a rail system, boasting a main span of 1,408 meters. The height of the bridge's towers is also a significant achievement, soaring over the water at more than 322 meters, making it the highest suspension bridge in the world in terms of tower height. This record-breaking combination of width, length, and height elevates the Third Bosphorus Bridge to a level of engineering excellence that sets it apart on the global stage. During the construction phase and the subsequent operation phase, the project provided employment for nearly 7,500 people, reflecting its substantial scale and complexity. The bridge's construction required a massive amount of materials, with 720,000 cubic meters of ready-mixed concrete used for both the Third Bosphorus Bridge itself and the North Marmara Highway. Akçansa, a Turkish company, played a crucial role in the construction of this extraordinary bridge by producing special concrete and cement, ensuring its durability for over a century. The ability of the bridge to withstand various physical and chemical forces is a testament to the high-quality materials used in its construction. Notably, the Third Bosphorus Bridge represents a milestone in stay cable technology, employing a hybrid approach combining cable-stayed and suspension bridge designs. This innovative combination allowed for the construction of a bridge with a shallow deck, chosen for its aesthetic appeal and complementing the existing Bosphorus bridges. Overcoming the challenges of such an ambitious project, the bridge's completion in just 36 months was a remarkable achievement. The immense size and complexity of the bridge required the development and testing of new equipment capable of handling the longest and heaviest parallel strand cables ever manufactured. Freyssinet, a company involved in the project, produced ultra-high-strength strand cables, setting a global record with the use of 1,960 megapascals cable strand. A total of 176 stay cables, some over half a kilometer in length and containing 151 strands, were installed in the bridge, requiring rigorous quality control and innovative solutions to ensure structural integrity and durability. The unique combination of cable systems posed challenges that required the development of specially designed deviators to control cable alignment and prevent sagging. Additionally, managing excitation under wind loads demanded the use of hydraulic pistons with a stroke of plus or minus 920 millimeters to dampen the cable's movement while allowing them to respond freely to service loads. The main cable pulling process involved the installation of two main cable lines, which are integral to the bridge's structural integrity. These main cables bear the weight of the bridge deck and ensure its stability and safety for vehicular and railway traffic. The successful completion of 85% of the main cable lines, totaling a remarkable 13,000 tons, signifies a major achievement in the construction of the bridge. The process began with the preparation of the cable drums, which contained the individual strands that would form the main cables. The cables were composed of high-strength steel strands, meticulously arranged and tightly bound together to create a robust and resilient structure capable of withstanding the bridge's loads and environmental forces. With the cable drums prepared, the pulling process commenced. Specialized machinery, cable pullers and winches, were utilized to slowly and steadily pull the cables across the bridge's designated cable supports. As the cables were pulled, they were carefully guided and secured onto the bridge's towers and anchorages. This required a high level of precision and attention to detail to ensure the cables were correctly positioned and tensioned. Proper tensioning of the cables is critical to distribute the loads evenly and maintain the structural integrity of the bridge. The completion of 85% of the main cable lines, totaling 13,000 tons, is a significant achievement that showcases the expertise and dedication of the construction team. This milestone brings the project closer to its final stages, highlighting the remarkable progress made in the construction of the third Bosphorus Bridge. The third Bosphorus Bridge project has reached a significant phase in the construction, with the assembly process of the inclined suspension ropes nearing completion. These inclined suspension ropes are a crucial part of the bridge's suspension system, providing essential support to the bridge deck and ensuring its stability and resilience against various forces. The inclined suspension rope assembly process commenced after the successful installation of the main cables, which were meticulously pulled and tensioned across the bridge's towers and anchorages. These main cables serve as the primary support structure for the bridge deck, and the inclined suspension ropes add an additional layer of stability and strength to the overall suspension system. The ropes themselves are made of high-strength steel wires, engineered to withstand significant tension and loads. The construction team worked with specialized equipment, cable pullers and winches, to draw and position the inclined suspension ropes in a controlled and systematic manner. To begin the assembly process, the inclined suspension ropes were unwound from massive cable drums. These drums held thousands of kilometers of steel wire, which were carefully arranged to form the inclined suspension ropes. Each rope was meticulously inspected to ensure its integrity and adherence to strict quality standards. With the ropes ready, the assembly process began at specific intervals along the main cables and bridge towers. The ropes were anchored securely to the main cables and attached to the bridge's deck, creating a network of suspended support that complements the overall suspension system. The inclined suspension ropes were installed at a calculated angle, which helps distribute the weight of the bridge deck evenly across the main cables. This angle also contributes to the bridge's ability to absorb and dissipate dynamic forces, such as wind and traffic loads, ensuring the stability and safety of the structure. As the assembly process progressed, the construction team closely monitored the tension and alignment of each inclined suspension rope. Advanced sensors and measurement tools were used to gauge the tension levels accurately, and any necessary adjustments were made to maintain uniformity and balance within the suspension system. To date, an impressive 5,500 kilometers of inclined suspension ropes have been drawn in the assembly process. This remarkable feat of engineering showcases the expertise and dedication of the construction team, highlighting the careful planning and execution required to complete such a complex task. The lifting gantry crane used for this project is an impressive structure consisting of two parts. These parts were meticulously designed to work in tandem, ensuring optimal lifting capacity and stability. The first part is the main gantry frame, which forms the backbone of the crane. The second part comprises counterweights and lifting equipment, essential for balancing the crane during operations and for the precise vertical movement of heavy bridge segments. The assembly process of the lifting gantry crane began with the transportation of its components to the construction site. These components included the massive main gantry frame, counterweights, lifting hoists, cables, and other essential parts. The main gantry frame, with its intricate network of beams and supports, was skillfully erected and securely anchored to a stable foundation. Next, the counterweights, which play a vital role in balancing the crane, were strategically positioned. Proper distribution of the counterweights ensures the crane can handle the significant weight of bridge segments during the construction process, minimizing any risk of instability. With the main frame and counterweights in place, the lifting equipment, including hoists and cables, was meticulously installed and thoroughly tested. These components are responsible for the precise vertical movement of the crane's lifting mechanism, ensuring smooth and controlled lifting operations. The lifting gantry crane's impressive carrying capacity of 3,000 tons makes it capable of handling the immense weight of bridge segments and other construction materials with ease. Its robust design and state-of-the-art engineering ensures safe and efficient lifting operations throughout the project. The successful completion of the assembly process allows the lifting gantry crane to be fully operational and ready to undertake its crucial tasks in the construction of the third Bosphorus Bridge. With its substantial carrying capacity and precise positioning capabilities, the crane is now ready to handle the assembly and positioning of various bridge segments, including those for the third Bosphorus Bridge's main span and approach spans. The lifting gantry crane's completion marks a significant step forward in the overall progress of the bridge construction. It demonstrates the expertise and dedication of the construction team, who worked tirelessly to bring this vital piece of equipment to life. The successful assembly of the lifting gantry crane ensures the construction of the third Bosphorus Bridge is progressing steadily and is on track to become an iconic symbol of modern engineering excellence in Istanbul. The third Bosphorus Bridge stands as an engineering marvel, embodying the fusion of cutting-edge technology, Turkish engineering prowess, and innovative design. This iconic structure has not only enhanced transportation connectivity between Asia and Europe, but has also pushed the boundaries of modern engineering, leaving a lasting legacy for generations to come. The completed quantity of concrete works reached 39,582 cubic meters, representing an impressive 81.08% of the total required amount. This substantial achievement showcases the construction team's efficiency and dedication. Additionally, the steel works for Section 1 were fully completed, with a total quantity of 13,214 tons, ensuring the structural integrity and strength of the project. The concrete works for this section were fully completed, with a total quantity of 27,647 cubic meters. This accomplishment demonstrates the successful execution of concrete pouring, ensuring the foundations and structures are in place. In terms of steelworks, 10,974 tons were completed, which accounted for 53.96% of the required amount. While there is still work to be done, the completion of over half of the necessary steel works is a notable achievement for Section 2 of Kanwonnerski Island within the Petersburg Western High-Speed Diameter Project. Kanwonnerski Island, Section 3, demonstrated remarkable progress in both concrete and steel works. The completion of 51,525 cubic meters of concrete represented a significant milestone, reaching 87.82% of the total required amount. Moreover, the steelworks in Section 3 showed impressive advancement, with 16,851 tons completed, accounting for 85.58% of the required amount. Kanwonnerski Island, Section 4, Concrete works. The completed quantity of concrete works for Section 4 was 34,273 cubic meters, accounting for 91.13% of the required amount. Steelworks. The steelworks for this section amounted to 2,572 tons, representing 45.26% of the required amount. The Berg River Bridge, a remarkable engineering feat situated within the picturesque Valdivia state, stands as a testament to human progress and connectivity. Officially inaugurated on June 21, 2018, by the executive mayor of Drakenstein Municipality, Councillor Conrad Poole, the bridge has since become an iconic link connecting communities and enhancing accessibility. Martin Venter, the visionary founder and CEO of Valdivia State, expressed his pride during the opening event, highlighting the symbolic significance of bridge construction as a representation of human advancement. He emphasized the bridge's role in benefiting not only the estate's residents, but also the wider community. Stretching over the tranquil waters of the Berg River, the bridge forms a vital link between the Valdivia Estate and the R45 Simondium Road. This connection, established through the newly built Berg River Gatehouse, has significantly reduced travel times to key destinations. Commuters now enjoy a mere 30-minute journey to the Cape Town International Airport and the city itself, a 16-minute drive to Stellenbosch, and a mere 3 minutes to Paarl Main Road. Notable for its impressive scale and significance, the Berg River Bridge holds several intriguing facts. It proudly holds the distinction of being South Africa's first private bridge of such magnitude. With a length spanning an impressive 400 meters, flanked by roads on both sides totaling 1.2 kilometers, the bridge creates an essential conduit for efficient travel and transportation. The construction process of the Berg River Bridge was a monumental endeavor that spanned 2 years, culminating in its completion. The project required a substantial investment of approximately R100 million, reflecting the significance of this undertaking in terms of both engineering and community development. The construction process of the Berg River Bridge was a monumental endeavor that spanned 2 years, culminating in its completion. The project required a substantial investment of approximately R100 million, reflecting the significance of this undertaking in terms of both engineering and community development.
The Rosbrick Bridge, a vital transportation link connecting Moorsbach and Rosbrick, has undergone a remarkable transformation, culminating in its reopening after 7 months of extensive reconstruction. The bridge's history dates back to 1948, and its significance lay not only in its role as a roadway, but also as a structure spanning over crucial railway tracks, including the prominent Frankfurt-Paris line. The endeavor to rejuvenate the bridge was driven by necessity. Over the years, the bridge had deteriorated to a point where the specter of collapse loomed large. The risk was too significant to ignore, prompting authorities to embark on a massive project that demanded both financial investment and engineering expertise. The initiative, financed entirely by the department, amounted to a substantial sum of 4.7 million euros. This investment was not just for repairing the bridge, but entailed a comprehensive approach. The old, weakened structure was completely dismantled, paving the way for a new and robust incarnation. The renovation process unfolded in several phases, each carefully orchestrated to ensure a smooth transition and minimal disruption to the daily lives of commuters. Prior to the commencement of construction, traffic management strategies were implemented, beginning with restrictions on vehicles weighing over 3.5 tons. This was followed by alternating traffic for cars and vans once preparatory work commenced. A pivotal juncture in the reconstruction journey arrived during the Pentecost weekend. In an astounding feat of engineering prowess, a 72-hour race against time unfolded beneath the bridge. The railway line passing underneath, a part of the SNCF network, required a complete shutdown. Tracks and overhead wires were disassembled, allowing for the removal of the bridge's 1,400-ton concrete deck. This high-stakes operation was executed flawlessly, a testament to the skill and precision of those involved. The collaboration between various stakeholders was evident in the seamless execution of this intricate plan. The bridge was dismantled and relocated, making way for its eventual replacement. Train traffic was temporarily halted to facilitate the installation of the new deck, a process that spanned several weeks. Amidst the disruptions and challenges, the local community demonstrated resilience and adaptability. The road closure between Rossbrück and Morsbach had ramifications for local businesses. To address these economic impacts, local merchants and entrepreneurs united under the banner of an association named GEAR. This collective effort underscored the shared responsibility to mitigate the effects of the construction process on the region's economy. Finally, after months of construction, the Rossbrück Bridge emerged from its metamorphosis. On a Tuesday morning at 9:30 a.m., the president of the Departmental Council of Moselle inaugurated the new bridge. With the completion of final installations, including guardrails and safety rails, vehicular traffic was reinstated, heralding a return to normalcy for the communities it connects. The Rossbrück Bridge project stands as a testament to human ingenuity, determination, and collaboration. It encapsulates the dedication of those who worked tirelessly to ensure the safety and convenience of commuters while safeguarding vital transportation infrastructure. As vehicles once again traverse this route, they bear witness to the triumph of engineering and the resilience of a community united in the face of disruption.